Hello and welcome back. So here in this little video, we're going to change tack a little bit. We've looked at stable isotope mixing models, simple and through to very complex mixing models. Now we're going to look at some other information we can get from these stable isotope data. And specifically in this video, we're going to look at how we calculate the isotopic niche. We're not going to talk too much about the theory around the isotopic niche and what it means and what it doesn't mean. We've discussed that in the lecture, but now really we're going to talk about how we quantify this or how we calculate it. And predominantly we're going to do this using another OR package. And this one is Cyber, which is developed by Andrew Jackson along with some of his colleagues. I'm going to share some content and then we can get going. So I'm going to share my screen here. I'll drop that there down. And first of all, as before, we're going to start with, so what we've got a series of folders. We've got our cyber.csv, which is the input file we'll need to use. The OR project, I've already got it set up. And we actually, because they're very similar, we're going to run the niche stuff here, but we're also going to run the food web metrics in this exact same folder because we need the exact same input files. But that's the next video. So the first thing we want to do is just open up this cyber.csv and give you a look at what's in it. And it should be very similar because exactly what we have is it's almost the exact same as our prelim.csv. We've got the lake here, which is termed as community. We've got from some previous stuff where this used to have to be coded as a number. In fact, what I'm going to do, I'm just going to get rid of that, and then we don't need to worry about that. All right, let's just get rid of that altogether. Nice. Okay, so we've got lake here, which is defined as community, species or taxon, which here is called group, and we'll get to why we've changed those names in a moment. We've got the unique identifier, the code for that sample. We've got a classification tool, which will sort of come in, not so much in the niche, but when we move to the food web stuff, you'll understand why we have that. And we have two variables called ISO1 and ISO2. ISO1 is our carbon, ISO2 is nitrogen. If you have hydrogen and nitrogen, you can use those instead. One of the limitations of Cyber is it can only handle two isotopes or two tracers. There is other packages out there. There's one called Niche Rover, which I think can certainly handle 3 and possibly even 4 distinct tracers. But when we're dealing with Cyber, we're dealing just with 2 tracers, which are typically carbon and nitrogen. But if you have something else, you can use them. One thing I've used in the past is where if you run the post two-source mixing model. Remember, I mentioned that one of the benefits of that is that you can get individual values. So we could get a littoral or a resource reliance derived from carbon and an estimate of trophic position derived from nitrogen, put those in here instead and run the calculate niche, isotopic niche, but based off those values that have been corrected for baseline effects. Okay, let's get rid of that, and we're going to bring back in our OR project. Okay, so this again should be very familiar to everybody by now. We've got our OR Studio running with the Markdown file, and I should note here that, again, similar to the other stuff where we've used packages, I'm adapting stuff that's already out there. So a lot of this demonstration, say, was first pulled together by Andrew Jackson as part of the stuff he has around the Cyber project or Cyber package. And it's really like, I've taken their stuff and adapted it for our example, but I've included these links because it's really important that you take the time to follow these links. And there's a lot more information in them, and if you've got questions about how to apply this to your own project, chances are you're going to find it in there. And I'm pretty sure there's also a GitHub page that Andrew Jackson has set up around the cyber at the moment for new developments and new versions and whatnot. And again, if you've got questions, you can post them up there, and it means either Andrew or somebody else in the community can get back to you on it. Okay, so for now, to start the start, as before, we're going to load the packages that we're going to need. We're going to do a little bit of plotting as well, so I'm just loading ggplot. So let's cyber and ggplot. And then we want to bring in our data and just have a quick look-see. So we're going to start with cyber data. I'm just going to load that in and make a little figure here. Yeah, the head function, things like that we've seen before. So again, very, very similar to if we were just looking when we, right at the start of this, when we first plotted out this data, we've got Lake Kivi, Lake Vuontas. But here we've got things color-coded essentially by species name or by taxon name. And when we scroll down a little bit further, when we're specifically looking at the niche, we could look at this in any number of different species, but because we're particularly interested in the differences between these two species of fish, the LSR whitefish and the perch, we're just going to focus on those for the for this isotopic niche component. In the subsequent lecture where we're looking at food webs, we're going to come back to that. Okay, so next thing we need to do is create something here called cyber group. And essentially what we're doing here is we're just pulling out species of interest, subset from cyber data, group is LSR, and group is perch. And here, this is an important step. What we're going to do is we're going to pull out ISO 1, ISO 2, group, and community. And we're going to pull them out in that order. Okay, and let's have a quick look at that. Okay, so we can bring up our cyber group here. And we see here we've got ISO 1, ISO 2, group, and community. And group is species, community is lake. And this is the specific format that we must put the data in for cyber to be able to handle it. Okay, ISO 1, ISO 2, group, community in that format, and the cyber can handle, and the package can handle it. If you don't want to use that format, you can do all the math yourself. So let's plot out our species of interest here in our ggplot. And again, very similar to what we saw before, looking at the carbon and nitrogen distribution for these. Lake Kivi, perch, have these some perch feeding at a higher trophic level that we talked about before. Lake Vuontas, separation and the carbon axis there. So the first thing we can do is we can just put some ellipses around these data. We talked a bit before about why the ellipse is useful, or at least in class about why the ellipse is useful. And here, just using a little function in ggplot, we can add standard ellipses to these data. And again, so each of these ellipses include 40% of the data, which is broadly equivalent to a standard ellipse. So we can see that it's a tight representation of the distribution within that data point. Within each population. There is a lot of points outside it because we're only including or only basing it on 0.4, on 40%. We can change that and add another ellipse, 95% ellipse, say. And this ellipse is including 95% of the data points. And obviously, it's a much bigger ellipse. It's including more of the variability, and we'll see why it becomes. This is a really important point, because quite often, and we'll see later, if you want to use cyber, you can calculate overlap. You can calculate isotopic niche overlap between two species, or between two populations. But that overlap is really going to be dependent on the size, on the specific specifications you give for the ellipse. Do you want it to be a standard ellipse? Do you want it to include 95% of the points, 40% of the points? The bigger you make it, the greater the proportion of overlap is going to be. So if you're presenting these data, make sure that you state what size the ellipse is, or what the characteristics of your ellipse. And if you're reading somebody else's data, reviewing a paper or something like that, similarly, just keep an eye out for that, because you can. This is one of these things where what goes on underneath the hood kind of determines the output, determines the results. So something to be aware of. So we're going to start running some of these analyses now. And again, because the package is built to do all the heavy lifting for us, what we need to do is take our data here called cyber group and turn that into what's called a cyber object, which is essentially just something that's the correct format for the package to handle. So we're going to click that. So create something here now called cyber G example, and that is our cyber group. And then we can do some figures. We can do some plotting with this within the actual cyber package. At the moment, a lot of this is kind of based around base OR, but I do believe they are updating it at the moment to be more sort of a ggplot flavor to it. Okay, so here we're looking at both lakes plotted together and both species plotted together. A lot of overlap. We can see here where we've got the ellipses, 95% ellipses fitted to the data, where we've got the convex hulls also been fitted to the data, but a lot of overlap as well. So not the clearest way to present the data. Certainly this isn't what you want to be putting in the figures or in a paper. But again, it's just showing you how the cyber is handling the data. One moment, excuse me. Okay, so next thing we might want to do is to get some of these actual metrics out. Yeah, so we can run this group ML, which is giving us the group metrics on CyberG example, and then print that to have a look at it. Let's click go. So we've got, because we're dealing with the group metrics here rather than the community metrics, we've got 3 distinct values that the package is going to give us. And these are split up by each of our groups. We've got whitefish in Lake Kivi, perch in Lake Kivi, whitefish in Lake Vuontas, perch in Lake Vuontas. We've got TA, which is the total area, which essentially is the convex hull around all the data points. We've got the SEA, which is the area of the standard ellipse around all the data points. And we also have this small sample size corrected SEA, the SEAC, which is described in Jackson's paper. And if you're dealing with smaller sample sizes, anything below sort of 20 individuals, I'd suggest, or maybe even 30 individuals, SEAC is probably where you want to be, what you want to be using. And if you're doing a comparison between species and you've got lots of sample individuals for one, a few for another, definitely SEAC is what you need to be using. A quick thing to note here, you'll see that the data are given to 5, 6 decimal places. Again, we're dealing with isotope data. Your instrument precision is not going to go beyond 1 decimal place. So don't ever present these data at 6 decimal places because you're not that precise. As much as you might might want to be. So we've got these values, and I mentioned earlier that, so we've got, this is our estimate of what the SEA is for each of these species, each of these groups. We can do some looking at the overlap between these different species. And like say we want to look at the overlap between LSR whitefish and perch in Lake Kivi. And here we're looking at maximum likelihood overlap. We can run that. Scroll down and we see we've got area for group 1, 2.6, area for, and these are typically the unit here, sort of per mil squared. Area 2 is 4.5, and the overlapping area between the two is around about 1.5. And if we scroll back up here, that's kind of makes sense that we've got a larger ellipse for perch than for whitefish, and we've got a reasonably large overlapping area between the two species. That's for a standard ellipse. Say we might want to have a look at the 95% ellipse, so a larger ellipse. Again, here, what we see, the area for both is greater, and the overlapping area kind of remains the same. If you look at it as a proportion, it should roughly remain the same. It's probably a little bit larger in this case. one thing we may want to do, and just to give you an example here, we can bring this down to 0.4, which makes it just about equivalent to the standard ellipse. And then we'll have a look back at that. And remember the values here are now 2.5, 4.6, 1.5, very similar to what we saw in the standard ellipse. So again, what we're measuring here in terms of overlap and niche width really is dependent on how you're characterizing your ellipse. I'm going to just bring that back to 95 for myself in the future. Future Brian will thank me. Okay, one thing you might want to do then is to have a look at the relative overlap of species relative to their overall niche width. And again, there's different, and we'll talk a bit about this in class, about how to handle this. And there's different rationales and different reasons you might want to go take different ways. But here's an option that we can sort of look at how much is the overlapping area relative to the total area occupied by both species. And we can do that for Lake Kiwi. And we've got a relative overlap as around about 25–26%. So essentially what that's saying is of the total isotopic space occupied by these two species, around about 25% of that is overlapping. And that's based off the standard ellipse. Yeah? If we change that, as we'll see in a moment, if we change that to 95% overlap, you'd expect that, well, let's see, will that increase? We want to repeat this for Lake Vuontas. So here we've got the exact same thing, Lake Vuontas, looking at maximum likelihood overlap between the two species. Zip, zilch, 0. We've got similar sized niches, but no overlap. And if we scroll back up here, that makes perfect sense. Looking at the standard ellipse between the two, there's no great overlap there. If we change that to looking at the 95% ellipse and run that there, now we'll see obviously the area for both has increased, but the overlap area, we now have overlap because we've increased the size of both of those. And we can look at the same thing in Vuontas if we want to look at this as a proportion, and again, here we're looking at standard ellipse. If we want to look at that relative to the isotopic space of both species, again, for the standard ellipse, it's 0. If we change that to the 95 ellipse, that will become greater than 0. Let's just put it that way. Yeah? So we can start working with this. We've got some sort of nice information out of our cyber stuff already. We can sort of get a point estimate on the ellipse area. We can get a point estimate on the amount of overlap. What we don't have is any estimate of the error around that or the variance around that. How confident are we in that ellipse size? And that's where the cyber stuff really comes into its own, because by taking a Bayesian approach, we can calculate these ellipses size based on multiple estimates of the population, the distribution of the population, and then estimate the variance in those ellipse sizes based off the posterior distributions. So let's just click that and run that, and it'll take a few seconds to run. It kind of goes through each group independently. And in a moment, shouldn't take very long. We've got a successful model. All ran okay. Everything looks good. Let's see up here. We don't see this. I'm not too sure. Okay, we're not seeing that there for some reason, but that's okay. Usually the model should populate over there and just show us that it's run, but it's not there right now, and I'm not going to worry about that right now. Okay, so what we might want to do, so we now have we've run the model. Let's have a look at the output from the model. So we're doing a couple of things in this step. We're pulling out the posterior ellipses using the cyber ellipses call, and we're calling that an object called SEAB, and then we're doing a cyber density plot on the SEAB. And essentially what we're seeing here is, in fact, I'm going to change this. Just want to run this one here on its own first. So we've got a lot of information here. We've got these sort of semi box plots or density plots, or yeah, they're not really density plots. Let's call them box plots for now. And we've got 4 groups plotted out here. We've got LSR whitefish in Lake Kivi, perch in Lake Kivi, LSR whitefish in Lake Vuontas, and perch in Lake Vuontas. And what we can say, so the circle points here, the black circles, is the mode value for the SEAB. So the SEAB is a distribution of about 10,000 values, and the mode value is shown there with that black single circle. If we then move out and look at through these grey gradations, we've got the 50% credibility interval first, then the 75% credibility intervals, and finally the 95% credibility intervals. So essentially what that means is that we're 95% certain that the actual SEA for whitefish in Lake Kivi falls somewhere between 2 and 3, let's say. We'll get the actual data points in a moment. But you see here where we've got a larger perch are somewhere between, let's say, 4 and 6. That where you can then be 95% certain that perch have a larger niche than whitefish. And if we scroll back up to our initial plot up here, that certainly makes a lot of sense because they've clearly got a much, much broader range in nitrogen. Similarly, we can look at what we see here in Lake Vuontas, and we see that the 2 species, perch probably have a slightly larger niche, but there's no great big difference. So certainly we're not 95% certain that the niche width of perch is greater than what we see for whitefish. One quick comment, I've got a couple of, and I've forgotten how to spell. Can we compare isotopic niche width between lakes? Can we say that LSR whitefish in Lake Vuontas have a larger niche than the LSR whitefish in Lake Kivi? They have a larger isotopic niche, we can certainly say that, but for the most part, we're not interested in that. We're interested in, are they feeding on a greater variety of prey? Are they ecologically more of a generalist in Lake whitefish? Are they ecologically more generalist in Lake Vuontas than they are in Lake Kivi? It's not so simple to answer that question because we need to be able to, these values, because we're looking at the actual isotope ratios, are incorporating baseline variability. And if we have 2 lakes where we've got much bigger carbon baselines between these 2 lakes, or a very big difference in carbon baselines between these 2 lakes, that will directly influence our isotopic niche width. But it may say absolutely nothing about dietary niche width. So we need to be really careful when you want to make inferences here about isotopic niche versus dietary niche. And we've talked a bit about this in class. So the last little piece I want to look at here is getting the actual data. So we know how to make the plots. If we do this in ggplot, or if we do this in or Studio, we could just save that figure as a PNG if that's what you want to do, or you can use the essentially the typical way to save figures in OR. I'm seeing as we haven't actually done this, I'm just going to very quickly show you how to do that. dev.new, and let's say we want to save that as a PDF, and we want to call it cyber. Let's call it cyber group. So BER underscore grp dot PDF. And then we want to turn dev dot off afterwards. So if we just run that, and it's a while since I've done this, so fingers crossed it's going to work. We can then go back to our folder in here, and we should have, we do, cyber.group saved as a PDF, okay? And that's, you can tidy that up a little bit. You can do whatever you want to do with that before you put it in your paper. Yeah, one thing to note here, one thing we didn't do earlier was, I didn't mention earlier, I'm just going to pull those back out there just for simplicity's sake. Is this nice little touch here where we can actually add the SEA values, or SEAC values, as a red cross onto our SEAB plot, yeah, by going back to our group ML. Remember that group ML thing that we produced back up here? Here, group.ml. So what we're doing is we're taking the SEAC values and we're adding them to this plot. And typically you want to see your SEAC values being pretty similar to the mode SEAB values. If they're way out, probably a good sign that you've got very small sample sizes or there's something not quite right. So that's something just to, again, it's a nice thing to run in your data. Just have your own confidence that everything is working as it should be. Okay, we want to get to the raw numbers. So here's just a series of different little bits of script to give us some output from this. And we can run this through, and essentially, so first we've asked it for the modes, and then we've asked it to give us the credibility intervals. So we've got the mode value and series of credibility intervals for variable 1, 2, 3, 4. Scroll back up here, variable 1, kiwi and LSR whitefish and kiwi, 2, perching Lake Kiwi, 3, 4, 2 species in Lake Vuontas. And again, here we're looking at the mode SEAB value, and then the lower and upper 99%, 95%, and 50% credibility intervals. Yeah. So you can do this. You can extract those data, put them in a table, put them in your figure, or put them in your table, put them in your paper, present them. Really good idea to present them that way with the mode and the actual credibility intervals, and maybe your sample size and other things like that that you want to put in your summary tables. Quite often things like this, I'll have sample size, carbon isotope ratios, nitrogen isotope ratios, means and standard deviations, and then you can add these values into the exact same table. It's a nice way of putting it all together. Okie dokie. I want to bring this back up here. Bring that back up here. And that pretty much is Cyber for calculating the isotopic niche. It's pretty easy, pretty straightforward, works easy, it's cool data. So next little video, we're gonna flip that around and do, it's almost the exact same steps, but it will give us those food web metrics or the layman metrics that we discussed in the lectures. Okie doke. Hope you enjoyed that. Hope it worked. Bye.